Collision theory states that for a reaction to occur, particles must collide with enough energy to overcome the activation energy and in the correct orientation. Remember, the activation energy is the minimum amount of energy required for a reaction to occur. We're now going to look at the Maxwell-Boltzmann distribution. In terms of your Y and X labels, X will be energy and Y is the number of molecules with a particular energy. So the Maxwell-Boltzmann curves have a very particular shape, one which looks like this. And it's important that you can recognize what different parts of the graph are telling you about the particles or molecules' energy. So down here, because E is very low, we can say that some particles have very low energy. And the reason for that is the collisions that occur cause these molecules to slow down. Be aware that there are no particles with zero energy. The peak of a Maxwell-Boltzmann distribution curve is representative of the most probable energy that the particles have. It's important that you can identify that in the exam. Point C on the graph is the mean energy. This is higher in value compared with the most probable energy, and the reason for that is there's no upper limit to the energy a particle can have. We're going to label the activation energy EA. So to remind you, this is the minimum amount of energy the particles require for a reaction to take place. So that means that anywhere to the right, it means that the particles that exist here have the sufficient energy required to react when they collide. Notice that the curve never meets the x-axis again, as there is no maximum energy a particle can have. So to reiterate, down here, there are no particles with zero energy. The peak represents the most probable energy. C is the mean energy, and this is higher than the most probable energy. You'll often find the activation energy marked on, and that means that any particle existing to the right, so in this part of the curve, must have enough energy to react when the particles collide. D represents the fact that the curve never meets the x-axis, as there is no maximum energy a particle can have. Now we need to consider the effect of temperature on the Maxwell-Boltzmann distribution. So we're going to start with our original curve. We're going to call this T0 because that's our original temperature. What happens now if we were to lower the temperature? And then what happens if we were to increase the temperature? So I'm going to call this one T1 and T2. So let's describe and explain what's happening at T1. So T1, that's when the temperature is lower than the original temperature. We still need to show that activation energy, so I'm using my dotted red line to represent the minimum amount of energy required for the reaction to occur. So at the lower temperature T1, what can we see about the graph? We can see that the peak of the curve is higher and to the left of the original curve. What about our pink line T2? Remember, that's the higher temperature. Well, to describe the graph, we can see that the peak is lower and to the right. So let's really try and explain, particularly with that higher temperature, what's going on. I'm hoping you can see by just filling in this portion of the graph under the curves, you can see that when you increase the temperature, much more particles have energy greater or equal to the activation energy, and this means that there are more successful collisions in a given time, meaning that the rate of reaction increases with higher temperature. And they do love to ask you this in the exam. So our explanation, so at higher temperatures we have higher rates of reaction. What is our explanation for this? Many more molecules or particles have energy equal to or greater than the activation energy. So more successful collisions occur per unit time. So just be prepared to draw these graphs. Here's your original temperature. As I said, if the temperature is lowered, you'd expect that peak to be higher and to the left, meaning fewer molecules have energy equal to or greater than the activation energy. By increasing the temperature, what happens is many more molecules have sufficient energy to overcome the activation energy, and you'll see that peak displaced to the right and being slightly lower. The total area of each of these curves, remember, must equal the same because the number of particles doesn't change. I don't want to talk about this too much because after all it's a recap of GCSE and IGCSE chemistry knowledge. We've already discussed, however, the effect of temperature on the rate of a chemical reaction and how we can use the Maxwell distribution curves to represent this. So we've talked about how increasing the temperature means that the particles have more kinetic energy and therefore collisions are more frequent per unit time, and you're more likely to have particles with energy equal to or greater than the activation energy. Increasing the concentration merely means having more particles in the same volume, so the successful collisions are more frequent per unit time. Increasing the surface area through making a solid a powder, for example, this will mean that more collisions occur per unit time, increasing the rate. Increasing the pressure means that there are more gas particles in the same volume, so successful collisions are more frequent. We'll now have a quick look at the effect of adding a catalyst. So here's our Maxwell-Boltzmann distribution again. We have the number of molecules on the y-axis, the energy here. Now what adding a catalyst does is it reduces the activation energy, hence why you can see that line representing the activation energy has moved to the left. And what that means is that you have many more molecules with the energy which is either equal to or greater than the activation energy. Look, the area of this part of the curve has increased. The shape of the curve, however, remains the same because after all, we haven't altered the temperature. And here's your simple definition of a catalyst. It's a substance which increases the rate of a chemical reaction without being chemically used up or changed. This question is about the Maxwell-Boltzmann distribution of molecular energies in a sample of gas shown in the figure below. Which letter best represents the mean energy of the molecules? Remember, the mean energy occurs slightly to the right of the peak, so the answer here is C. What does the area under the curve represent? It's the total number of particles, so you do really need to know what the various parts of the graph are telling you. The answer here is B. The diagram shows below a Maxwell-Boltzmann distribution for a sample of gas at fixed temperature. EA is the activation energy. On this diagram, sketch the distribution for the sample of gas at a higher temperature. So what did we say? We said that the peak would occur to the right and slightly lower. They'll be looking for you to start that curve at the origin, which I've done. So yeah, I'm happy with that. With reference to the Maxwell-Boltzmann distribution, explain why an increase in temperature increases the rate of a chemical reaction. So by increasing the temperature, you increase the number of molecules with energy greater or equal to the activation energy, meaning that there are more successful collisions per unit time.